Right now, as you watch this, somewhere in the world, a data center the size of multiple football fields is consuming enough electricity to power a small city. Not to run the internet, not to stream video, not to process payments, but to think, to run artificial intelligence. And the company making most of that possible is one that the majority of people have never bought a product from, never downloaded an app from, and couldn't pick out of a lineup. And yet, without it, the AI revolution as we know it would not exist. But before we get there, let's talk about what's actually happening. When you type a message into ChatGPT and a response appears within seconds, when a self-driving vehicle processes a chaotic intersection, or an algorithm knows what you want to watch, what you're witnessing is not magic. It's the result of billions, sometimes trillions, of mathematical calculations happening simultaneously across thousands of specialized processors. Now here's what most people never see. They see the interface. They see the chatbot. What they don't see is the infrastructure that makes it possible. And sitting at the very center of all of it, quietly, invisibly, powering nearly every major AI system in the world, is a company called Nvidia. In June 2023, Nvidia became only the third company in American history to cross a $1 trillion market capitalization. It became the most valuable business on earth. How does a company most have never interacted with become the engine behind the most transformative technology shift of our generation? That is the question we are answering. So the real question isn't just, what is Nvidia? The real question is, how does a company that most people have never directly interacted with become the engine behind the most transformative technology shift of our generation? If you want to understand how technology truly works, not just the surface layer, but the systems and decisions that shape the future, subscribe to Strategy Lens. This is exactly what we do here. Subscribe to join the lens. Let's get to work. To understand why Nvidia matters, and why it matters this much, we need to go back to a fundamental assumption baked into computing from the very beginning. That assumption was this: a computer should solve problems one step at a time. For most of computing history, this made perfect sense. The CPU, the central processing unit, was designed around a philosophy of sequential execution. You give it a task, it works through it step by step, with extraordinary precision. Imagine a master chef, one of the best in the world, precise, fast, experienced. He can prepare almost any dish you ask for, but he works through a recipe sequentially. Chop the onions, then sauté them, then add the stock, then reduce, one step, then the next. But now imagine you need to cook for 50,000 people simultaneously, all different dishes, all ready at the same time. One chef, no matter how brilliant, cannot do that. The architecture itself is the problem. In the early 1990s, a new category of software began pushing computing hardware in a direction it was never designed to go. Video games, specifically 3D video games. Rendering a single frame of a 3D environment requires calculating position, lighting, shadow, and depth for millions of pixels. Simultaneously, at 60 frames per second, a game engine needs to perform these calculations roughly 2 billion times per minute. Think of it like a highway with a single lane. It doesn't matter how fast each car is moving. If a million cars need to pass through at the same time, they all queue up. You don't need faster cars, you need more lanes. That's the insight that changed everything. This is the moment where everything changes, not, how do we make the processor faster? But, what if we used a completely different kind of processor? What if instead of one incredibly powerful brain working sequentially, you built something with thousands of smaller processors? Each simpler and less powerful individually, but all of them working at the same time. That class of problem, 20 years later, would turn out to describe almost every major workload in modern artificial intelligence. This inefficiency wasn't just a limitation, it was a signal, and one company heard it louder than anyone else. In 1993, 3 engineers left a meeting at a Denny's diner in San Jose, California, with a napkin, an idea, and $30,000 between them. One of them was a 30-year-old named Jensen Huang. The idea they were sketching out was not, on the surface, revolutionary. They wanted to build better graphics chips for personal computers. That was the pitch. That was the visible part. But underneath that pitch was a philosophical conviction that set Jensen Huang apart from everyone else in the industry. A conviction that most would have considered premature or completely wrong. The conviction was this: the future of computing would not be won by making single processors faster. It would be won by making thousands of simpler processors work together. To appreciate how contrarian that belief was in 1993, you need to understand the orthodoxy he was pushing against. The entire industry was organized around a single idea. The CPU is the brain of the computer. Intel was spending billions on ever faster processors, but Jensen Huang looked at that roadmap and saw a ceiling, a point at which the sequential model would become fundamentally insufficient. Imagine you're given the task of counting every grain of sand on a beach. You could hire the smartest, fastest counter in the world, but it would still take an unimaginable amount of time. Or, you could divide the beach into 10,000 sections and have 10,000 people count simultaneously. None of them individually is doing anything impressive, but together, they finish the task in a fraction of the time. That's parallel computing, not one powerful brain working sequentially, but thousands of simpler processors working simultaneously, each handling a small piece of a much larger problem. Nvidia spent its first 6 years iterating, building graphics chips, learning the hardware, and quietly refining its architectural philosophy. Then, in 1999, they released something that changed the industry. Nvidia marketed it as the world's first GPU, the Graphics Processing Unit. A deliberate rebranding that signaled something important. This was not just a faster graphics card. This was a new category of processor. The GeForce 256 was the first piece of hardware demonstrating that a massively parallel architecture could outperform a sequential one. Not in a laboratory, but in millions of living rooms, running in real time. The proof of concept wasn't published in an academic paper, it was shipped in a retail box. In 1999, Nvidia was a graphics company, full stop. Their roadmap was built around frame rates and visual fidelity. What they had was something more valuable than a plan. They had an architecture. One perfectly suited for problems the world hadn't fully discovered yet. That decision, to move beyond graphics, would be the most consequential in Nvidia's history. It had a name, and we'll get to it in part 3. By the mid-2000s, Nvidia was the dominant force in graphics hardware. The GeForce lineup was powering the most visually advanced games on the planet. Revenue was growing, the roadmap was clear. And in almost any other company, leadership would have looked at that success and doubled down on the thing that was working. Jensen Huang did something different. He looked at the immense parallel processing power sitting inside every Nvidia GPU, power used almost entirely for graphics, and asked a question that nobody in the graphics industry was asking. What if we let anyone program this hardware? For anything. In 2006, Nvidia released CUDA, the Compute Unified Device Architecture, and while that name means relatively little without context, the decision behind it was one of the most strategically significant moves in the history of technology. At the time, GPUs were locked behind a graphics API. If you wanted to use a GPU, you had to speak its language. This was technical, but awkward and deeply limiting. The power was effectively trapped behind a graphics-only interface. CUDA broke that wall. It provided a programming model that allowed engineers to write software that ran directly on the GPU, treating it not as a graphics accelerator, but as a general-purpose parallel computing engine. For the first time, you could write in a familiar language and execute across thousands of cores simultaneously. Here's the best way to picture what CUDA did. Imagine the GPU as a massive, incredibly powerful factory floor. Thousands of workers capable of extraordinary output. But the factory only had one kind of machine: graphics machines. The entire floor was set up to do one specific job. CUDA is what converted that factory floor into a general-purpose facility. Now those same workers, using those same machines, could be assigned any repetitive, large-scale task. Not just graphics, scientific simulations, financial modeling, drug discovery, and eventually, artificial intelligence. The workers didn't change. The machines didn't change. What changed was the ability to assign them new kinds of work. This was not just an API. It was a complete programming paradigm. And then, Nvidia did something equally important. They invested deeply in building the ecosystem around CUDA. Libraries optimized for linear algebra, cuBLAS. Libraries for deep neural networks, cuDNN. Tools for profiling, debugging, and optimizing GPU-accelerated code. They didn't just open the hardware, they built the entire development environment on top of it. When researchers at the University of Toronto trained a deep convolutional neural network called AlexNet on Nvidia GPUs in 2012, they didn't just win the ImageNet competition, they won it by such a margin that it functionally ended the debate about whether deep learning was viable. AlexNet was trained on two Nvidia GTX 580 GPUs. Without CUDA, that training would have taken weeks on CPU clusters. On those two consumer GPUs, it took days. The AI era began in a university lab, running on gaming hardware. The research community noticed immediately. Papers citing GPU-accelerated deep learning began multiplying. Labs switched to Nvidia hardware almost overnight. CUDA became the default environment, not because Nvidia forced it, but because nothing else came close. The CUDA ecosystem created a powerful moat that competitors struggled to replicate, not because of hardware alone, but because of the depth of the software layer built on top. These weren't just wrappers. They represented years of hardware-specific optimization. There's a concept in technology strategy called platform lock-in. The idea that once enough developers build on a platform, the switching costs become prohibitive. The entire ecosystem, the frameworks, the libraries, the talent pipeline, was built on CUDA. Switching away from Nvidia wouldn't just mean buying different chips. It would mean rebuilding a decade of infrastructure from the ground up. It's like the difference between a store and an ecosystem. Apple doesn't just sell phones, it sells an environment that makes leaving feel costly. Nvidia did the same thing in AI infrastructure, years before the boom made it obvious. In 2006, CUDA was a niche tool. By 2012, it was the foundation. By 2020, it was the default infrastructure of an entire industry. The long-term strategic bet had paid off with the quiet, compounding accumulation of dependency. And the world was just beginning to understand what that dependency actually meant. By the early 2010s, something was shifting in the world of artificial intelligence, something that most people outside the research community couldn't yet see, but that would reshape technology, business, and society within a single decade. AI had existed as a field of research for more than 60 years, but for most of that time, it had been constrained by two fundamental limitations: not enough data and not enough compute. The internet changed the first. By the 2010s, humanity was generating a torrent of information that, with the right tools, could be used to train machines to understand, predict, and generate. The data problem was solved by the internet. The compute problem, that was going to be solved by Nvidia. To understand why, we need to understand how modern AI systems actually learn. At the core of virtually every major AI application today, from language models to autonomous driving, is a structure called a neural network. A neural network is a system loosely inspired by how the human brain works. Imagine billions of tiny switches organized in layers. Through millions of adjustments, a process called training, the network learns through repeated exposure and correction. Technically, a neural network is a parameterized function composed of layers of linear transformations. Training involves forward and backward propagation, computing the gradient of the loss and updating parameters. The dominant computational primitive is the matrix multiplication. And here is the critical connection that explains everything about Nvidia's dominance. Training a neural network is, at its core, an exercise in performing the same mathematical operation, matrix multiplication, billions of times. That workload, repetitive, massively parallel, operating on large arrays of floating point numbers, is precisely the class of problem that GPUs were designed to handle. Not because anyone designed GPUs with AI in mind in the 1990s, but because the mathematical structure of rendering pixels and the mathematical structure of training neural networks are, at a fundamental level, the same. The numbers illustrate this convergence with startling clarity. AI compute demand has been growing at a rate that makes Moore's law look slow, and every petaflop of that demand runs on GPU clusters. The performance advantage of GPUs over CPUs for deep learning workloads is not marginal. It is transformational, a difference of several orders of magnitude for the specific operations that dominate AI training. The effect on AI development was immediate and profound. Model sizes considered unreachable became the new baseline. Timelines that researchers had measured in years contracted to months and then to weeks. For Nvidia, the timing was extraordinary. They had built infrastructure capable of serving the boom when it arrived. The world had come to Nvidia's architecture, not the other way around. Understanding that GPUs are essential for AI training is one thing. Understanding exactly how the software that developers use every day connects to that hardware, that's where the depth of Nvidia's advantage becomes truly clear. Because Nvidia's dominance is not just about having powerful chips, it's about having built the only complete, deeply optimized software stack that sits between the AI developer and the GPU hardware. A framework is the layer of software that AI researchers use to build and train models. The most widely used, TensorFlow and PyTorch, function as the primary interface. Think of a framework like an architect's design software. The architect doesn't build the structure themselves, they design it and hand the plans to construction teams who execute the building. If TensorFlow is the architect, designing the system, specifying what needs to be computed, then CUDA is the construction manager, coordinating thousands of workers to build it simultaneously and efficiently. But CUDA is not the only layer. Sitting between the framework and the raw runtime are specialized libraries. The most important is cuDNN, which provides hardware-optimized implementations of every fundamental deep learning operation. These aren't just wrappers. They represent years of hardware-specific optimization that cannot be reproduced quickly on alternative platforms. There is also a broader point about network effects. Every major AI framework was built with CUDA as its primary backend. Every AI researcher learned using tools that assumed an Nvidia GPU. Every benchmark, every research paper, every production system built on CUDA. The ecosystem wasn't just supported by it, it was shaped by it. By the late 2010s, a new reality was becoming impossible to ignore. The AI systems being built were growing at a rate that no existing infrastructure was designed to support. Model sizes were doubling, tripling, and then multiplying by orders of magnitude. Year after year, demanding fundamentally more sophisticated approaches to how GPUs were organized. A single server with a few GPUs was now laughably inadequate. Jensen Huang gave the required solution a name that captures exactly what it is: the AI factory. Not a data center in the traditional sense. Not a server farm built to store information. Something entirely new. A facility engineered for the industrial-scale production of intelligence. A traditional factory takes raw materials and uses machinery to produce a finished product. An AI factory does exactly the same thing. Data is the raw material. GPU clusters are the machinery. Trained AI models are the product. Unlike traditional static workloads, AI training is dynamic, iterative, and deeply interconnected. A training run involves tens of thousands of GPUs communicating constantly, synchronizing updates without slowdown. To train GPT-4, OpenAI reportedly used a cluster of over 25,000 Nvidia GPUs for months. The estimated energy consumption was equivalent to the annual electricity use of 4,500 American homes. Nvidia's role extends far beyond selling GPUs. They provide the networking fabric, the system software, and the reference architectures to build these facilities. In the AI factory era, Nvidia is not a component supplier. It is the industrial partner. What makes an AI factory fundamentally different from a traditional data center is the nature of the workload it runs. Traditional data center workloads, web hosting, database queries, email routing, file storage, are largely static. They execute discrete transactions and process requests independently. The workload is well understood and modular. It can be scaled by simply adding more standard servers. AI training is none of those things. It is dynamic, iterative, and deeply interconnected. A training run for a large language model may run continuously for weeks or months. It involves tens of thousands of GPUs that must communicate constantly with one another, sharing intermediate computations and synchronizing gradient updates. Every GPU must maintain consistency across the entire model, all while operating at maximum utilization with no tolerance for slowdown. This is not just computing, it is industrialized intelligence production at scale, and Nvidia is the only company that sells you every layer of it. To truly understand what Nvidia has built, and why it is so difficult to replicate, we need to go inside the AI factory itself. Past the marketing language, down to the physical and architectural reality. At the most fundamental level, an AI factory is composed of tens of thousands of GPUs organized into clusters, but simply placing them in proximity achieves nothing. The challenge, and the engineering art, lies in how these GPUs communicate, how they share data, and how they coordinate computations across a system of almost unimaginable scale. The foundation is Nvidia's current flagship, the H100. These are not gaming GPUs repurposed for AI. They are purpose-built compute accelerators, engineered from the transistor up. The H100 SXM5 contains 80 billion transistors. For context, the human brain contains approximately 100 trillion synaptic connections, but operates on fundamentally different principles. The H100 delivers up to 3.9 petaflops of tensor performance. It can transfer the equivalent of the entire Library of Congress, digitized, in approximately 2 seconds. That is the speed of data flow. The H100 introduced the transformer engine, hardware specifically designed to accelerate attention mechanisms. It dynamically switches precision to maximize throughput while maintaining stability. It also introduced NVLink 4.0, providing 900 gigabytes per second of bidirectional bandwidth. In a DGX system, all 8 GPUs are connected in a fully connected mesh. This allows them to operate as a single logical compute unit rather than 8 separate accelerators. This is the heart of Layer 1. Layer 2. Intra-node communication, NVLink and NVSwitch, inside a single AI server. Connecting multiple GPUs efficiently is a problem that standard interfaces were never designed to solve. PCIe, the interface that connects most components in a modern computer, offers approximately 64 gigabytes per second of bandwidth. For a GPU transferring data to another in the same server, that becomes a critical bottleneck. NVLink solves this. It is Nvidia's proprietary high-speed interconnect, connecting GPUs within a server at bandwidths that dwarf PCIe by an order of magnitude. NVSwitch extends this by creating a fully connected mesh across all GPUs in a system, meaning any GPU can communicate with any other GPU at full NVLink bandwidth simultaneously. This enables collective communication operations to execute at near memory bandwidth speeds. The synchronization across all 8 GPUs introduces almost no overhead relative to local computation. This is a concrete performance advantage. Layer 3. Inter-node communication, InfiniBand, and quantum networking. A single DGX server is insufficient for training frontier AI models. The largest training runs require clusters of thousands of these servers. And when you cross the boundary to inter-node communication, from connecting GPUs within a server to connecting servers within a cluster, the networking challenge becomes dramatically more complex. The dominant technology for this fabric is InfiniBand, a standard Nvidia now controls through its acquisition of Mellanox. That acquisition was one of the most strategically precise moves Nvidia has ever made. Nvidia didn't just buy a networking company, it gained control of both ends of the GPU to GPU communication stack, the chip that generates the data and the network that moves it. In large-scale AI training, the performance of the entire cluster is determined not by the fastest GPU, but by the slowest communication link. By owning the fabric, Nvidia could co-design the GPU and the network as a unified system. This vertical integration appears repeatedly at every layer of the AI factory stack. It is an advantage competitors simply cannot replicate. Layer 4. Orchestration and the software control plane. With hardware in place, GPUs, NVLink, InfiniBand, the next challenge is coordination. When a training job spans 10,000 GPUs across hundreds of servers, something must manage how work is distributed, how resources are allocated, and how failures are handled. This is the orchestration layer, the software control plane of the AI factory, and it is arguably as important as the hardware beneath it. Think of orchestration software as the air traffic control system for the AI factory. At a major airport, air traffic control ensures that every aircraft is exactly where it needs to be at the right time, without collision or delay. A single coordination failure can cascade into chaos. The orchestration layer does the same thing, but for computational workloads. It ensures every GPU is assigned the right work, and that when something goes wrong, a server fails, a GPU crashes, the system recovers automatically, and training continues without starting from scratch. The orchestration layer is the brain of the factory floor. Now, let's look at the final layer, the physical infrastructure. Layer 5, the physical infrastructure. Beneath the software, the networking, the chips, is the physical reality of running a system at this scale. And the physical constraints are, in some ways, the most humbling part of the story. A single DGX H100 server, one server, 8 GPUs, consumes approximately 10 kilowatts of power. A rack of these servers can consume 100 kilowatts or more. A training cluster of 10,000 GPUs draws 30 to 40 megawatts of power continuously, comparable to a small town's electricity demand. And it converts most of that power directly into heat. Managing that heat is not a secondary concern, it is a primary engineering constraint. Traditional air cooling, the approach used in most data centers, becomes economically and physically impractical at these power densities. The future of AI factory cooling is liquid, direct liquid cooling of GPU components, immersion cooling for entire servers, and purpose-built thermal management systems that treat heat rejection as a first-class architectural requirement alongside compute and networking. This is the physical reality of the AI era. It is built on power and managed by liquid. This is layer 5. What actually happens when a company like OpenAI trains a large language model? The process is more intricate and more interconnected than most descriptions capture. It is dependent on precise coordination at every step. Let's walk through it in detail. Stage 1. Data preparation. Training begins long before a single GPU is activated. The raw training data, hundreds of billions or trillions of tokens, must be scraped from books, websites, and scientific papers. This data must be cleaned, deduplicated, tokenized, and serialized into a format that training infrastructure can consume efficiently. This phase is computationally intensive. Deduplication alone, removing near-identical documents, requires algorithms running across large CPU clusters for days. The quality of this process directly affects the quality of the trained model. Garbage in, regardless of how many GPUs you run it through, produces garbage out. Once data is prepared, the next critical decision is how to distribute the training job across the available GPUs. Let's look at stage 2. Once data is prepared, the next critical decision is how to distribute the training job across available GPUs. For a model with hundreds of billions of parameters, this distribution is a fundamental prerequisite. These models are far too large to fit in the memory of any single GPU, even an H100 with 80 gigabytes of bandwidth. Real large-scale training requires 3 distinct parallelism strategies. Think of training a massive AI model like assembling an enormous piece of furniture, so large that no single workshop could contain it and no single team could understand every part. Data parallelism means making multiple copies of the assembly instructions and having different workshops assemble the same piece simultaneously with different components, then combining their progress. Model parallelism, specifically tensor parallelism, means dividing the assembly plan itself. Different workshops handle different sections of the same piece simultaneously. Pipeline parallelism means organizing the workshops into an assembly line where each workshop performs its specialized task and passes the work downstream. Real training uses all 3. The interaction between these 3 dimensions is the primary systems engineering challenge. Nvidia's Megatron LM framework pioneered the 3D parallelism approach that combines all 3. These optimizations are deeply tied to Nvidia's hardware communication primitives. This is stage 2. Now, let's go inside the training loop. With data flowing and parallelism configured, the training loop begins. Each iteration of the loop, called a training step, follows the same basic structure, repeated billions of times over weeks or months. Each GPU performs the forward pass, producing a prediction. The prediction is compared against the known answer using a loss function. Then the backward pass begins, computing the gradient of the loss to adjust every parameter. Then, gradients must be synchronized across all GPUs. In a cluster of thousands, this involves transferring terabytes of data through the network fabric, which is why NVLink and InfiniBand matter enormously. Imagine 10,000 students all working on the same incredibly complex puzzle. At the end of each round, every student must share what they learned with every other student, so the whole puzzle comes together at a speed no one could achieve alone. Stage 4. Monitoring, checkpointing, and stability. A training run is not a single uninterrupted process. It must be actively managed to prevent instabilities that can derail a run consuming millions of dollars. Engineers watch for loss spikes or plateaus, checkpoints, snapshots of the entire model state. are saved at regular intervals, so if a failure occurs, training can resume rather than starting from the beginning. At this scale, hardware failures are statistical certainties. A cluster of 25,000 GPUs will experience a failure roughly every 8 hours. Systems must recover automatically, often in minutes rather than hours. What emerges at the end is a trained model, a set of trillions of numbers that encode patterns from the data. That is what an AI model is at its core. Numbers. And nearly everyone was shaped by Nvidia hardware. At this point in the story, Nvidia is no longer simply a hardware company that makes chips which AI companies happen to buy. Something more significant has occurred, something that changes the nature of the competitive dynamic entirely. Nvidia has become infrastructure, not in the casual sense of the word, but in the precise, technical, and strategic sense. The same way that a city's water supply or electrical grid is infrastructure, not a product you choose between alternatives, but a foundational layer that everything above it depends on, and that cannot be replaced without rebuilding everything built on top of it. Imagine a city that was built over 50 years, with a specific type of plumbing infrastructure running through every building, every street, every home. The infrastructure works extremely well, but now imagine a new plumbing standard emerges that might be slightly more efficient. Can the city switch? Technically, yes. Practically, you would need to demolish and rebuild the plumbing in every building simultaneously, retrain every plumber, replace every fixture, and manage the transition without disrupting water service to anyone. The cost and disruption are so enormous that even a technically superior alternative struggle to gain adoption. Nvidia's position in AI infrastructure is structurally identical. The plumbing is CUDA, cuDNN, the frameworks, the tooling, the institutional knowledge, and it runs through everything. The real game is the infrastructure, and for now, there is nothing else at scale that can replace it. Consider what a company would actually have to do to replace Nvidia in their AI infrastructure stack. First, they would need alternative GPU hardware that matches or exceeds Nvidia's performance on the specific mix of operations their workloads require. This is difficult, but achievable. Google has TPUs, Amazon has Trainium, Intel has Gaudi, AMD has MI300X, but performance parity is the easy part. They would also need to port every model, every training script, every inference pipeline from CUDA to the alternative platform's programming model. In a large AI organization, this represents years of accumulated engineering work, tens of thousands of lines of optimized code, and institutional expertise. They would need equivalent replacements for every CUDA library, for cuDNN, for cuBLAS, for NCCL, at a level of optimization that matches Nvidia's decades of hardware-specific tuning. Not approximately, not almost. The performance must be equivalent, because in AI training, a 10% throughput reduction translates directly into 10% higher compute costs. Costs are already measured in the hundreds of millions. The switching cost calculation becomes even more complex when you account for the Model Zoo problem. The vast majority of pre-trained model weights available publicly, from Hugging Face's repository, from research labs, were trained on Nvidia hardware with CUDA. In 2023, Nvidia's data center revenue reached $47.5 billion, a figure that exceeded the total annual revenue of companies like Twitter, Snapchat, and Zoom combined. When your competitors invest billions to reduce their dependence on you, you know you've achieved something remarkable. You've become a strategic risk in someone else's roadmap. No strategic position, however dominant, is permanent, and Nvidia's position, for all its extraordinary strength, comes with genuine vulnerabilities, structural risks, and competitive dynamics that will shape the next decade of AI infrastructure in ways that are still unfolding. Understanding these limitations is not pessimism, it is the complete picture, and it is, arguably, the most important part of this story. Risk 1. The cost problem. Nvidia's GPUs are extraordinarily expensive. An H100 costs between $25,000 and $40,000 per unit. And in some periods of acute supply shortage, resale prices have exceeded $70,000. A cluster of 10,000 H100s represents a capital investment of $250 million to $400 million in GPU hardware alone, before accounting for servers, networking, power infrastructure, real estate, and operating costs. This cost structure has profound implications. Academic researchers, smaller companies, and organizations in developing economies face access barriers that are not primarily technical, they are financial. The implications for who controls the direction of AI and who benefits from it are not just economic, they are geopolitical. As of 2024, the top 5 AI companies collectively account for the vast majority of frontier AI training runs. The cost of training has increased from roughly $5,000 for GPT-2 in 2019 to estimates of $100 million or more for the most recent models. At that cost structure, the number of organizations capable of participating without external capital is effectively zero. Risk 2. The energy and sustainability problem. The energy consumption of AI infrastructure is not a secondary concern or a long-term worry. It is an immediate material constraint that is already shaping where AI factories can be built and how quickly they can be scaled. Data centers currently consume approximately 1 to 2% of global electricity. AI-specific compute is growing at a rate that makes AI one of the largest single consumers of electricity on Earth. Major technology companies are already facing power availability as a primary constraint. The limiting factor is simply, the grid cannot support it. Microsoft has announced plans to restart the 3 Mile Island nuclear plant. Google is investing in small modular nuclear reactors. The energy problem is not theoretical. Risk 3. The geopolitical problem. Nvidia's supply chain depends on Taiwan Semiconductor Manufacturing Company, TSMC. TSMC manufactures Nvidia's H100 and Blackwell chips on its most advanced process nodes. There is no alternative fabrication partner capable of producing these chips at comparable performance. This creates a geopolitical concentration risk that has not gone unnoticed by governments. The United States has imposed sweeping export controls on advanced Nvidia GPUs. China accounted for an estimated 20 to 25% of Nvidia's data center revenue before export controls. The restrictions have effectively cut Nvidia off from one of the world's largest AI markets. Nvidia's geopolitical exposure is, in a very real sense, one of the most significant strategic risks it faces, not a competitor winning on technology, but a government decision removing a market. Perhaps the most technically interesting risk Nvidia faces is the possibility that the architecture of AI itself changes in ways that reduce the advantage of its current hardware. The transformer architecture, which currently dominates large language models, happens to be extraordinarily well suited to Nvidia's GPU architecture. Dense matrix multiplications, regular memory access patterns, predictable parallelism. These properties align almost perfectly with what GPUs do best. But AI research is not static. Alternative architectures, sparse models, mixture of experts, state-space models like Mamba, have different computational profiles. Some of these are less dominated by dense matrix multiplication. Some have irregular memory access patterns that GPUs handle less efficiently. The Mamba architecture is an instructive example. Its core computational primitive, selective state-space model computation, has a sequential dependency structure. That makes it less amenable to the same kind of parallel execution that transformers support. Nvidia's tensor cores provide less of an advantage for these workloads. If sparse or recurrent architectures gain traction at scale, Nvidia's hardware-specific optimization advantage becomes less decisive. The combined weight of these risks has produced a competitive response, unlike anything the semiconductor industry has previously seen. AMD, Intel, Google, Amazon, Microsoft, and a constellation of AI chip startups are all pursuing Nvidia's position from different angles and with different architectural bets. AMD's MI300X has achieved genuine competitiveness with the H100 on certain workloads and has been adopted by major cloud providers. Its primary limitation remains the software ecosystem. ROCm, AMD's CUDA equivalent, lacks the depth and optimization level of CUDA for most production AI workloads. Though the gap is narrowing, the question is not whether Nvidia will face competition. It already does, and it will intensify. The question is whether the depth of the CUDA ecosystem, accumulated over 18 years of developer investment, can be replicated on a timescale relevant to the current AI build-out. So when we step back from the technical detail, from the chip specifications and the networking protocols, and look at the larger shape of what Nvidia has built, what do we actually see? We see a company that made a series of bets that most of its contemporaries considered either premature or irrelevant, and turned out to be correct about each one, with a precision that seems almost impossible in hindsight. The bet that parallel computing would matter beyond graphics. Correct. The bet that AI would eventually require exactly the kind of infrastructure Nvidia was building. Correct. That is not luck. That is a specific kind of institutional intelligence. The ability to see structural inevitabilities that others dismiss as speculation, and to build toward them before the market demands it. But here is perhaps the most important realization of all. Artificial intelligence is not primarily a software problem. It is an infrastructure problem. Nvidia is building the equivalent infrastructure for intelligence, not the light bulbs. Those are the algorithms, but the power grid that makes the light bulbs possible at scale. Nvidia is not just a chip company, it is the company that built the computational substrate on which the intelligence of machines is being constructed. Like electricity in the early 20th century, it operates quietly, invisibly in the background. Most people have no idea that Nvidia exists. And yet, the AI they interact with every single day would not exist without it. That is the true measure of infrastructure. Not visibility, not fame, indispensability. Because the companies and researchers who understand the real game are the ones who will be best positioned to navigate whatever comes next. And now, you understand it too. If you found this analysis of Nvidia's infrastructure moat valuable, please leave a like and subscribe to Strategy Lens. We go deep where others stay on the surface. By subscribing, you help us continue creating these high-retention documentaries on how money and power truly work. Thank you for watching Strategy Lens, and we will see you again next week.